This is a pre-built version of the application. So we'll have five peers, and this will be the first one, second one, number 3, and 4, and this would be the eavesdropper peer. So 4 communicating peers and 1 eavesdropper, and they would be communicating with signed messages. So this will be picking up messages from the other 4 peers, and this one will be picking up messages from the other 3 communicating peers, and this one, same thing. And this, and this one. So those 4 peers will be using the elliptic curve digital signature algorithm to sign and verify the signature on messages, and this eavesdropper peer would want to sign messages pretending to be Alice, Bob, Carla, or Dave. And I put the test data that we will be using here. So we'll be using this curve used by Bitcoin, and here we have it in decimal format, and we have here the same curve with the same numbers but in hex format, and we'll also use this curve, and same thing here, we have it in decimal format, and we have the same numbers in hex format here. And since we are running in hex mode, let's go ahead and pick up those values. So A, B, P, N, and H for the curve, for the SEP 256 K1 curve in hex format. And we'll have this this peer and this one. Use this curve. With this generator point. And let's say this one picks this secret key, and this one picks this secret key, and we'll have those two use the other curve, this one. So we'll get the domain parameters for this curve. And the generator point. And we'll have this one, pick this secret key, and this one, pick this one. And Eve here can see all those domain parameters for each one of the peers, and the generator points, so the y and x coordinates. For the generator point, and also the public key, the y and the x coordinate for the public key for each one of the peers. So here, when Alice entered her private key, she went ahead and calculated her public key, which is this many hops, so the private key, from the generator point. And she sent that public key to the other three communicating peers, in addition to having sent the domain parameters and the generator point. And the other three peers do the same thing as Alice. So Alice now has public keys for Bob, Carla, and Dave, and Bob has public keys for Alice, Carla, and Dave, and Carla has public keys for Alice, Bob, and Dave, and Dave has the public keys for Alice, Bob, and Carla. And let's say that Alice wants to send and sign this, wants to sign and send this message to the other three communicating peers. And let's say she picks this ephemeral key, and this is her private key, but let's say she enters an invalid key. So all other three communicating peers realize that the message was not signed with Alice's private key. So same for Carla and Dave. Now let's do the same thing, except let's go ahead and sign the message with a valid private key. So here we go. So they validate that message and realize that it was signed with Alice's private key. So they receive the signed message, the R, lowercase r, and S, and they use those. So first, SHA-256 is used to hash the message, and then we calculate W, U1, U2, and the point P, which is U1 times the generator of Alice, plus U2 times the public key of Alice, and we get V, and since it is congruent to R in mode N, then the message was signed with Alice's private key. So same here, Carla does the same thing, and Dave does the same thing. And let's say Carla wants to send a message. So let's say she used this ephemeral key, and let's have her use her valid private key. So each one of the other three communicating peers realized that the message was signed with Carla's private key. And when Carla, or before she sends the message, she hashes it and picks the ephemeral key and calculates the point R, and then calculate S, and sends the message in addition to lowercase r, and S, to the other communicating peers. And here Eve can see all three communications, those two originating from Alice, the invalid one and the valid one, and the one originating from Carla. But in order to sign those messages as being Alice, she needs to solve, or Eve needs to solve, the ECDLP, elliptic curve discrete logarithm problem, and compute the private key for Alice, D, or her ephemeral key, and same for Carla, to sign a message as being Carla. Now we could have used this data in decimal format, and to do that, all what we had to do is to change this to base 10. And the source code here will be available for download. Also a longer and comprehensively explained version of this prototype project. Including writing the code, will be available for watching by all channel members.